Chapter 3, Designing Cathodic Protection Systems. In Chapter 2, we explored the principles of cathodic protection and the various methods that are used to control corrosion by controlling the electrical environment around a metal surface. In this chapter, we will focus on the design of cathodic protection systems, including how to calculate the necessary current density, how to select the appropriate anodes and rectifiers, and how to install and test the system. Designing an effective cathodic protection system requires a thorough understanding of the factors that can impact its performance, including the type of metal to be protected, the environment in which it is exposed, and the size and shape of the area to be protected. It also requires the use of appropriate calculation methods and consideration of safety and maintenance issues. In the following sections, we will discuss these and other considerations in more detail and provide guidance on how to design an effective cathodic protection system. We will also explore the importance of testing and monitoring cathodic protection systems to ensure that they are operating as intended and providing sufficient protection to the metal surface. Section 3.1, Calculating Current Density. In order to design an effective cathodic protection system, it is important to determine the necessary current density required to provide sufficient protection to the metal surface. Current density is a measure of the flow of electric current per unit area of the metal surface and is typically expressed in milliamperes per square meters. There are several methods that can be used to calculate current density, including the Ohm's law method, the polarization curve method, and the computer modeling method. Ohm's law method. This method is based on Ohm's law, which states that the current flowing through a conductor is directly proportional to the voltage applied and inversely proportional to the resistance of the conductor. By measuring the resistance of the metal surface and the desired voltage, the necessary current density can be calculated using the following formula. Current density is equal to voltage divided by the resistance. Polarization curve method. This method involves measuring the corrosion potential and current density at various applied voltages, and plotting the results on a graph known as a polarization curve. The intersection of the curve with the corrosion potential line indicates the necessary current density to provide protection to the metal surface. Computer modeling method. This method involves using computer software to model the electrochemical reactions that occur on the metal surface and to predict the necessary current density to provide protection. This method can be useful for complex structures or for analyzing the performance of cathodic protection under different conditions. Which method is used will depend on the specific characteristics of the metal surface, the environment in which it is exposed, and the available resources. It is important to consult with a cathodic protection expert and to use appropriate calculation methods to ensure that the necessary current density is accurately determined. Example problem. A steel pipeline is to be protected by cathodic protection. The resistance of the pipeline is measured to be 10 ohms and the desired voltage is 50 volts. Calculate the necessary current density to provide protection to the pipeline, using metric units. Solution. Using the formula for current density from the Ohm's law method, we can calculate the necessary current density as follows. Current density is equal to 50 volts divided by 10 ohms, which comes out with 5 amperes per square meter. This is the necessary current density to provide protection to the pipeline. Note, it is important to ensure that the units for voltage and resistance are consistent when using the Ohm's law method to calculate current density. In this example, the units of voltage are in volts and the units of resistance are in ohms. The units for current density are in amperes per square meter. If you use imperial units, then the resistance is measured per foot and the current density will be amperes per square foot. Section 3.2, Selecting Anodes and Rectifiers. In galvanic cathodic protection systems, the anodes play a critical role in providing protection to the metal surface. Anodes are made of more active metals, such as zinc or aluminum, and are used to provide a path for the flow of electric current from the anode to the metal surface. When the anode is more active than the metal surface, it will corrode preferentially, protecting the metal surface from corrosion. There are several factors to consider when selecting anodes for a cathodic protection system, including type of metal to be protected. Different types of metal have different corrosion potentials and may require different types of anodes to provide effective protection. Environment. The environment in which the cathodic protection system will be used can impact the performance of the anodes. For example, anodes may be more prone to corrosion in certain environments, such as in salt water or in soil with high levels of acidity. Current density. The necessary current density, as determined by the design calculations, will determine the size and quantity of anodes needed to provide sufficient protection. In addition to selecting the appropriate anodes, it is also important to choose a suitable rectifier for the cathodic protection system. Rectifiers are used to convert alternating current, AC, to direct current, DC, which is required for galvanic cathodic protection systems. The rectifier should be sized appropriately for the current requirements of the system and should be capable of operating in the environment in which the cathodic protection system will be used. In impressed current cathodic protection systems, anodes are not used in the same way as in galvanic systems. Instead, the anodes are used to provide a path for the flow of direct current from the rectifier to the metal surface. The anodes in impressed current systems are typically made of platinum or titanium, which are resistant to corrosion. The size and quantity of anodes will depend on the necessary current density and the area to be protected. Procedure for selecting anodes and rectifiers. Determine the type of metal to be protected. The type of metal to be protected will determine the corrosion potential and the appropriate type of anodes to use. Assess the environment. Consider the environment in which the cathodic protection system will be used, including factors such as the pH of the soil or water, the temperature, and the presence of any corrosive substances. Calculate the necessary current density. Use appropriate calculation methods, such as the Ohm's law method or the polarization curve method, to determine the necessary current density required to provide protection to the metal surface. Select the anodes. Based on the type of metal to be protected, the environment, and the necessary current density, choose the appropriate type of anodes for the cathodic protection system. Select the rectifier. Choose a rectifier that is appropriately sized for the current requirements of the system and capable of operating in the environment in which the cathodic protection system will be used. Review and confirm the selection. Review the selected anodes and rectifier to ensure that they are appropriate for the specific application and environment, and confirm the selection with a cathodic protection expert if necessary. Example: a cathodic protection system is to be designed for a steel pipeline that will be buried in soil with a pH of 7. The necessary current density for protection has been calculated to be 4 mA per square meter. Determine the type of metal to be protected. The metal to be protected is steel. Assess the environment. The pH of the soil is 7, which is neutral. The temperature and presence of corrosive substances are not known. Calculate the necessary current density. The necessary current density has been calculated to be 4 mA per square meter. Select the anodes. Based on the type of metal, steel, and the neutral pH of the soil, zinc anodes could be used for the cathodic protection system. The size and quantity of the anodes will be determined based on the necessary current density of 4 mA per square meter. Select the rectifier, or rectifier that is capable of converting AC to DC and that is appropriately sized for the current requirements of the system should be selected. The rectifier should also be capable of operating in soil with a pH of 7. Review and confirm the selection. The selected anodes, zinc, and rectifier should be reviewed to ensure that they are appropriate for the specific application and environment. It may be advisable to confirm the selection with a cathodic protection expert. Section 3.3 Installing and Testing Cathodic Protection Systems. Once the necessary design calculations have been performed and the appropriate anodes and rectifiers have been selected, it is important to properly install and test the cathodic protection system to ensure that it is functioning correctly and providing adequate protection to the metal surface. The installation of a cathodic protection system will depend on the specific design and requirements of the system. In general, the following steps should be followed. Prepare the site, clear the area where the cathodic protection system will be installed and ensure that it is safe to work. Install the anodes, position the anodes in the designated locations and secure them in place, following the manufacturer's instructions. Install the rectifier in a suitable location, following the manufacturer's instructions. Connect the anodes and rectifier. Connect the anodes to the rectifier according to the design of the cathodic protection system. Test the system. Perform tests to ensure that the cathodic protection system is operating correctly and providing adequate protection to the metal surface. These tests may include measuring the voltage, current, and resistance of the system, as well as measuring the corrosion potential of the metal surface. Adjust and fine-tune the system. If necessary, adjust the settings of the rectifier or make other modifications to fine-tune the performance of the cathodic protection system. It is important to follow proper installation and testing procedures to ensure that the cathodic protection system is operating effectively and providing adequate protection to the metal surface. It is also important to regularly monitor and maintain the cathodic protection system to ensure that it continues to function properly over time. Example: a cathodic protection system is being installed for a steel pipeline that will be buried in soil. The system consists of zinc anodes and a rectifier. Prepare the site. The area where the cathodic protection system will be installed is cleared and checked for safety. Install the anodes. The zinc anodes are positioned in the designated locations along the pipeline and secured in place according to the manufacturer's instructions. Install the rectifier. The rectifier is installed in a suitable location, following the manufacturer's instructions. Connect the anodes and rectifier. The anodes are connected to the rectifier according to the design of the cathodic protection system. Test the system. Tests are performed to ensure that the cathodic protection system is operating correctly and providing adequate protection to the pipeline. These tests may include measuring the voltage, current, and resistance of the system, as well as measuring the corrosion potential of the pipeline. Adjust and fine-tune the system. If necessary, the settings of the rectifier are adjusted or other modifications are made to fine-tune the performance of the cathodic protection system. Here is a sample check sheet in chart format that can be used to record the steps and test results for installing and testing a cathodic protection system.